Hey everybody, it's Jenny from Norman S. Wright. A few weeks ago, I got to guest speak for a mechanical engineering class at Cal Poly, and I talked about heat pumps and electrification and decarbonization of buildings. And I thought these would be some good topics to talk about here as well. So I want to talk today about why heat pumps are going to be a big part of electrification and decarbonization in buildings. So let's get started. I did a video on electrification and decarbonization a little while back, so I won't go into the details about what they are. But as a refresher, decarbonization means the reduction of carbon, specifically the reduction of carbon dioxide, CO2 emissions. And electrification refers to the conversion of a system to the use of electrical power. So why do we want to electrify and decarbonize? Well, to eliminate emissions, to slow climate change, to improve air quality, and to obtain energy independence are just a few of the reasons. Let's move this over now. About 40% of the U.S. energy consumption is from buildings, and HVAC, refrigeration, and water heating make up a significant portion of that. Water heating is about 5%, refrigeration is 5%, cooling 9%, ventilation 11%, and space heating 32%. So in total, these categories are about 62% of the energy consumption of commercial buildings. Buildings also account for 30% of the greenhouse gas emissions, and building stock is expected to double by 2060, so it's just going to get bigger. Let's slide this over again. If you go back before the 70s, we built buildings that use gas and electric equipment. And then in the 1970s, the energy crisis hit, and ASHRAE 90.1 came out, and it drove us toward efficient buildings. To decarbonize, we need to eliminate all on-site and source carbon emissions. But before we can do that, we've got to get to all electric buildings, including the HVAC system, so that in the future we can use energy sources like wind and solar to power these systems. So all electric is the path to decarbonization. So let's move this over again. So what can we electrify in the HVAC and hot water systems? Well, we can replace gas boilers for space heating and for domestic hot water. Electric systems provide heat more efficiently. For a gas boiler, one therm input will give you about 0.8 to 0.98 therms of output heat. One therm is equal to 100 cubic feet of natural gas. This makes them between 80 and 98% efficient. Let's call it 90% efficient. An electric resistant heater is essentially 100% efficient. So if you put in 1 kilowatt hour of energy, you'll get 1 kilowatt hour of heat out. So this is 100% efficient. But a heat pump's coefficient of performance, the COP, which is a measure of its efficiency, can be 3.0 or higher. So if you put in 1 kilowatt hour of energy to run it, you can get 3 to 4.5 kilowatt hours of heat out of it. So a COP of 3 to 4.5 is essentially saying it's 300% or more efficient. So let's slide over again. Heat pumps are highly efficient because they move heat rather than generate it by burning fuel. In cooling mode, a heat pump operates exactly like the refrigeration cycle. I won't go into the details of the refrigeration cycle because there's a whole separate video on it, but let's draw the components. You've got the compressor, the condenser, the expansion valve, and the evaporator. And let's duplicate this over here for heating so we can talk about that next. In cooling, the refrigeration cycle works in this direction. So let's start at the compressor. The refrigerant is compressed in the compressor, raising its temperature and pressure. Then it releases heat to the outside as it flows through the condenser coil. So you're rejecting heat over here. Then it passes through the expansion valve, reducing its pressure and temperature. And then finally, air is blown over the coil in the evaporator, which cools the space. Now this warmer refrigerant goes back to the compressor and it does it all over again. Now if we look over here in heating mode, the flow of refrigerant is reversed using a reversing valve. So starting at the compressor again, the hot refrigerant comes out of the compressor, and instead of releasing the heat to outside, it's sent to the inside coil. Air blows over the inside coil and heats the space. From here, it goes to the expansion valve where the pressure is reduced and the cold refrigerant is sent to the outside coil. Now, the refrigerant is colder than the outside air temperature, so instead of rejecting heat, it absorbs it from the outside air. And then it goes back to the compressor where it starts all over again. So even if it's cold outside, the refrigerant is colder and it can pick up heat from outside and move it to the inside. Let me make a little bit more room. This is why heat pumps can have a COP of 3 to 4, or if you want to call it in terms of efficiencies, 300 to 400%. Let's slide this over one more time. Another thing to look at is operating costs. Electricity is more expensive than gas. So if we do some quick math, if we have a gas boiler that's about 90% efficient, you would have to put in 3.8 therms of energy input to get out 3.4 therms output, which is the equivalent of 100 kilowatt hours of heat output. At $2.21 per therm, this would translate to $8.40 per 100 kilowatt hours of heat output. Now, if we look at an electric boiler, which is 100% efficient, you would put in 100 kilowatt hours input to get out 100 kilowatt hours of heat output. And at 42 cents per kilowatt hour, that's $42 per 100 kilowatt hours of operation. And now let's look at the heat pump. With a COP of 3, you would put in 33 kilowatt hours of input energy to get out 100 kilowatt hours of heat output. And again, at 42 cents per kilowatt hour, this comes to $13.86 per 100 kilowatt hours. We're not factoring demand charges, but a heat pump operating cost will be proportional to COP. So you could see 1/3 to 1/4 the operation cost of an electric boiler. Let's bring everything back on screen now. So you can see why heat pumps are going to play a major role in electrification and decarbonization. Don't forget to like and subscribe to our YouTube channel, and thanks for watching.